Mm-hmm.
All right. Well, welcome back to our second installment of our Universe of Learning webinar with the Smithsonian affiliates. Today, we're going to be putting the universe in context, a tour. So we'll get to see all that's out there in the universe, visible universe, that is. Mary, next slide. There we go. Just as a reminder to who we are, I'm Erica Wright. I'm an education specialist from the Smithsonian Astrophysical Observatory. We have Mary DeSalt with us as well. From our Space Telescope Science Institute, we have Tim Rue. Brandon Lawton couldn't be here with us today, but he sends his regards. He's off learning to be an even better science communicator. We also have our Smithsonian Affiliations team. Today, Patty Artiega is here with us. Caroline and Christina are also part of the team should you ever need to access them. And we have a special subject matter expert today with us, Dr. Gabriel Brommer from ESA Aura Astronomer at the Space Telescope Science Institute. He's going to tell us a little bit about his work with frontier fields towards the end of our webinar. Very excited to have him here with us. All right. And then do one more slide, just so you all know what's coming up. So Mary's going to take us on a brief history of the views of the universe, and then take us through a tour of the visible universe. Following that, we're going to think about the farthest visible stars and galaxies. That's where Dr. Brommer is going to join in. And then Tim's going to share some further resources and next steps. All right, back to Mary.
All right. Without further ado, of course, we want to kind of put the universe in context for our visitors and for all of you. And the questions asked by NASA's Universe of Learning missions and research efforts are really universal questions. They've been asked by humans forever, and I have on the screen here a picture of one of the oldest maps or mental models of the universe that we know about. It's about 5,000 years old, a Babylonian map, and what is present-day Iraq, people created maps to represent not only their immediate surroundings, but their place on Earth and the constellations as well. And of course, asking these big questions about where we are in the universe has been a project of every culture during every time, and I like to kind of remind us of that when we're starting off thinking about what we now know, our current scientific understanding of the universe. In this slide, we have a couple different representations of ancient astronomical knowledge. On the left is a Chinese map from the 11th century of the constellations. And in fact, this map is known to have a star on it, which is a new star, a supernova that was observed by the Chinese and many other cultures in the year 1054. So that's kind of neat. In the middle of the screen is a temple in Palenque, a Mayan temple. And this, I don't know if you can see my cursor, but this series of glyphs actually represents, tells an origin story of the universe and represents the serpent of the Milky Way. The Mayans saw the Milky Way in the sky as being a serpent. And on the right is, on the screen, is an image of, actually by a woman who is from the 11th century, an 11th century nun named Hildegard of Bingen. And you can see in this, hang on for a second here. Let me see if I can. If you look closely at that, the Earth is at the center. Up above that, this represents the moon. This represents a lot of knowledge at the time. These two are the planets, known inner planets, Mercury and Venus. This is thought to represent the sun, and then we have Mars, Jupiter, and Saturn. And you'll see the Earth is at the center and all the stars around. So I wanted to give a nod to the fact that not only many cultures, but many genders have contributed to science as well. So that new star I mentioned in 1054 was not only recognized by the Chinese, but this rock painting from the Anasazi culture in Chaco Canyon in New Mexico is thought to represent that same new star in the sky, which today the Hubble telescope sees as the Crab Nebula. And we'll come back to that Crab Nebula a little later in the webinar. So many cultures exploring and making their own mental models, their own ideas of the structure of the universe before telescopes. And I'm going to now do kind of a brief history of the growth in our scientific knowledge of the structure of the universe. And before telescopes, many cultures accurately mapped the sky and predicted the positions, and some even predicted solar eclipses, something we've had happen recently, although that's a very tough thing to do until you have the ability to more accurately measure the positions and motions of celestial objects. So once the telescope started being trained on the heavens by Galileo and many people after, you started to be able to see things that kind of changed our model of what the universe is structured. We started to see that those 5 planets known by the ancients, Mercury, Venus, Mars, Jupiter, and Saturn, had some structure to them. They were not this picture on the upper right is a 1670 view drawing by actually Cassini, whom the Cassini spacecraft is named after, of Saturn, noticing this gap in the rings. And of course, we started placing the Earth not at the center of the universe, but as Copernicus suggested, perhaps at least the planets are revolving around the sun. Now, bigger and newer telescopes, as is true today, and as we'll find out through the webinar, lead to new discoveries. And one real example of this is William Herschel in the late 1700s. Was a really good telescope builder. He built these giant things. There's a picture of it on the left. But he also started mapping really thinking about where all the stars in the sky are and trying to place our solar system in kind of a 3-dimensional model. And this drawing in the upper right is Herschel's 3D model of the Milky Way galaxy, based on making estimates about the brightnesses of stars. And you can see he thought we were in this flattened system of stars. It's not quite how we understand the Milky Way today, but starting to get accurate. Herschel also made the first discovery of another planet in our solar system. And this is a Hubble image of Uranus, but Uranus is the planet he discovered. He did a lot of this work, again, with the assistance of his sister, Caroline. And actually, Caroline was more than an assistant. She really was a very important astronomer in her own right. She helped Herschel make extremely accurate measurements of stars, discovered many comets herself, but the the catalog. In fact, astronomers still use catalog numbers called NGC, New General Catalog numbers of galaxies. And many of those objects, fuzzy objects, were first observed by Messier and then by Herschel, and with Caroline carefully noting the positions and, in fact, fixing the positions. There were a lot of errors before her catalog. So astronomers are still using catalogs that depend on Caroline Herschel's work. But one of the things that Herschel started to note through the bigger telescopes and wonder about were all these fuzzy things. And some of you may have heard of Messier objects. Charles Messier started numbering these fuzzy objects to try and distinguish them from comets, which were also fuzzy through early telescopes. And there were all these different kinds of nebula, which were the fuzzy things. But a special class of them were called spiral nebula. And without being able to know how far they are, nobody knew quite what they were. There were theories that they were solar systems being born, or stars being born. But nobody knew, because we had no idea about the size of these things. And this debate, the nature of these nebula, continued right up through 100 years ago. In fact, 2020 is going to be the 100th anniversary debate, 100th anniversary of a big debate in astronomy, in our knowledge of where we are in the universe. And that debate was between Harlow Shapley, who's this guy on the left, and Heber Curtis, who's the guy on the right. And they were discussing the nature, in particular, of the spiral nebula and of the Milky Way galaxy. And so Shapley argued that the Milky Way galaxy was the entire universe. And Curtis argued that the Milky Way galaxy, that these other spiral nebula were other galaxies. Shapley thought the Milky Way was huge. Curtis thought it was relatively small. And so this debate couldn't be solved until there was a way to actually measure distances to these nebula. And in fact, the key to measuring that distance was another famous woman astronomer, Henrietta Leavitt, who's down here in the right. And she spent her time as one of the Harvard computers. These were a group of women astronomers downstairs from my office, right where I'm sitting, who spent their time looking at photographic glass plates. That's how images of the universe were recorded, studying them. And Henrietta Leavitt discovered, in fact, this is the plate. This is her writing on this glass plate. She looked at this special kind of star called Cepheid variables and determined a very key relationship that you could tell that this was a star that got brighter and dimmer, and the longer it took to get brighter and dimmer, the farther, the brighter intrinsically it was. And this was key to solving this debate between Curtis and Shapley. So a few years later, Henrietta Leavitt made that discovery in 1908, I guess. Edwin Hubble, using Henrietta Leavitt's key relationship, mathematical relationship between the period, the time these stars varied, was able to identify one of these variables. There's the glass plate where he identifies it in the Andromeda spiral nebula, and determined that spiral nebula must be far outside even Curtis Shapley's largest thoughts about the extent of the Milky Way. So this was the first idea. These galaxies were far distant, and Hubble went on to measure the distance to many galaxies, and not only that, but as we know, to determine that using spectra of those galaxies to determine their motions, and discover that oddly the galaxies were all racing away from us. The further they were, the faster they appeared to be racing away from us. A topic for another webinar. But now that we've done a brief history, I want to take you on a brief tour through the universe in size and scale. And to do that, we have to, the key thing that our audiences need to understand, and that is important to figure out, to think about, is to think of the universe at these three very different levels of scale. This kind of hierarchical structure of solar systems, which are stars with the stuff that orbits around them, planets and their moons, asteroids, other stuff. And of course, 20 years ago, we only knew of one of these, but now we know of thousands of these solar systems. But they exist inside of galaxies, which are at a far different scale than solar systems. And then the universe is a universe full of galaxies. So you have to think in those three realms. And a lot of people who will come to your organizations and your museums not really knowing the difference between a solar system, a galaxy, and a universe. After all, even in images, there's this idea of some spirally thing that's kind of disc-shaped. People can confuse them, but the scale differences between a galaxy, this is the Whirlpool galaxy imaged by the Hubble, and a solar system, the scale difference is really staggering. And so I want to start to use a model to help us really think about these size and scale differences, because those, let's see if I have this right here. Okay. Actually, let me go back here if I can. So solar systems are inside of galaxies, very big difference in scale, whereas galaxies compared to each other are relatively nearby each other. And so that's the scale we're going to explore in a more concrete way. So if we're going to construct our mental model of the universe, it has to kind of reflect what we actually see from the ground. This is a picture of those of you fortunate enough to live in dark skies. Maybe you've seen the Milky Way. I don't get to see it much in Boston here. But when we look up in dark skies, you see this dark band of stars and dust, and then stars kind of out from the side of that band. And so our model of how the universe is structured has to comport with that. So if we think of a galaxy as a city of stars, then our solar system is on the inside, and it's like being on the inside of a city where you can see all the bright lights around you, but you can't see the actual extent. And so our galaxy is a bit like that. This is an image. This is actually a panorama. It's as if you took your cell phone and went all the way around 360 degrees of our own galaxy. And again, like viewing a city from inside, and it's a flat kind of structure. You see this band of stars around you. But from the outside, you can look down on a city. Here's London from the International Space Station and see its structure. And likewise, you can look, this is not our Milky Way galaxy, again, because of course we're on the inside of it. This is another galaxy we think looks pretty much like our Milky Way galaxy. So I'm going to do the next few slides, our model. We're going to quickly go out to the edge of the universe. And if you happen to have a quarter, where's my quarter? Okay. And we're going to shrink our solar system down to the diameter of a quarter. So let's say out to Pluto. So this is going to be out to Pluto. And so if the solar system were shrunk to the size of a quarter, our Milky Way galaxy would actually be the size of North America. So that's the vast scale difference between a galaxy and a solar system. Our solar system is not in the middle of the galaxy. Here in our model, I want you to imagine stars scattered across the country, with the center of the galaxy somewhere. I think that's the Platte River in Nebraska. So we've got the center of the galaxy in Nebraska, and we've got our solar system actually somewhere there around Dallas, there where the Flight Museum is. So let's imagine that. If people could, in the chat box, make a quick prediction. If our solar system is the size of a quarter, how close would that next solar system be? Now, again, we kind of did that in the poll that we did at the beginning here. We said 2 grapes, so a good scale model. Oh, actually, that's the model of the sun. Sorry. That's not going to work. Because in my quarter model, the size of the sun is not a grape. The size of the sun is a microscopic dot on this quarter. Okay. The whole solar system is the size of the quarter. So the next nearest quarter solar system, Alpha Centauri, would be about 2 football fields away, 2 soccer fields. So imagine this Milky Way galaxy with specks of dust. That's the sun at the middle of these solar systems, spread out a couple of soccer fields apart all over the country and about 25 miles up, specks of dust. So it's about 25 miles thick, 2,500 or 3,000 miles across. That's our galaxy. I should note that in this poll, if we grew if the sun were actually the size of a grape, 2 grapes would be about 100 miles apart, would be the distance between them. So very vast distances between the stars, very vast distances between the stars. Okay. And solar systems, our own is quarter size, but they come in different sizes. And in fact, some of you may know of this recent solar system discovery of the TRAPPIST-1 system, much smaller than our solar system. In fact, our inner solar system, Mars and Earth, in our quarter size system scale would all be within this circle in the middle of the quarter. And the TRAPPIST system, the entire solar system would fit in our scale model. Compared to our quarter-size solar system, it would be the little ear. And if you happen to have a quarter, you can see the lobe of George Washington's ear. So that would be the size of the TRAPPIST system. All right. So now you have 300 billion stars, many of which have these planets around them. They're all specks of dust on a quarter-size solar system, 2 soccer fields apart. And now we can use our model to imagine where objects that we observe are. So here is famous image from the Hubble Space Telescope of the Eagle Nebula. And if we are located in our solar system here in Dallas, in our North American Milky Way scale galaxy, the Eagle Nebula would be, wait, I don't have my notes showing. It would be about a mile across, and actually, I can't remember the distance. Okay, I think maybe a few hundred miles, but I don't know this one. So let's go to the next one. The Pleiades. You know, that's a naked eye star cluster that we can see in the sky. These are two images, the one on the right taken by the Spitzer Space Telescope. All these images, by the way, are taken from a resource that Tim's going to talk about later. The Pleiades, this star cluster would be about the size of a shopping mall, a third of a mile across, about 10 miles away from our solar system in Dallas, right? The Orion Nebula, a little bit further, and both the Pleiades and the Orion Nebula would be away from the center of the galaxy. The Orion Nebula maybe 40 miles away from our little solar system quarter, and about 3/4 of a mile across. Then we look out into our galaxy and we see clusters of stars. This is a cluster of stars seen by the Hubble telescope that's actually close to the edge of the bulge of the Milky Way galaxy. It's called Westerlin 1. Here's another globular cluster of stars. Again, this is called M68. It's one of those fuzzy things observed by Messier back in the 1700s. It would be some 850 miles away from our solar system in Texas, so a very distant object within our Milky Way galaxy, kind of towards the bulge of the galaxy. In fact, a little bit on the other side of the bulge. Then, so we have some star birth regions. We saw some stars. Other things that our telescopes observe are dying stars. We can compare to our size and scale. This is a star that's really big, much bigger than the sun. Takes up a good chunk of our quarter, but it's dying, blowing off its material 80 feet away from it in our scale model. So this structure is much bigger than a solar system. The star is blowing out all its stuff. That Crab Nebula, object that was observed over 1,000 years ago by the Chinese and the Anasazi and several other cultures, in our Milky Way North American model would be about 160 miles away towards the edge, towards the edge of the galaxy, and about 1/4 mile across. Then towards the end of our tour, we're almost done with our tour. Here's another object we see, which is, this is an image taken with the Chandra X-ray telescope of the very center of our galaxy. And Chandra observed this flaring in the very center, which is that flare is the result of the giant black hole at the center of our galaxy swallowing material. And as the material, before it went into the black hole, it emits X-rays and you have that flare. That black hole at the center of our galaxy, even though it's a supermassive black hole, it has the mass of more than 4 million suns. It's about the size of a peppercorn. So much smaller than our solar system, about the size of a peppercorn at the center of our North American sized galaxy. So again, vast ranges of size and scale in our galaxy, but now we want to go outside the galaxy to the next galaxy. And for that, we have to jump levels again. So we're going to take that North American scale model of the galaxy we have in our heads, little specks of stars spread all around North America, 25 miles high, 2,500 miles across. We're going to shrink it down to a compact disk, because our galaxy is very flat. It's about 100 times more thin than it is across. So it's about the structure except for the bulge. I should have a bulge, a cotton ball in the middle of this, I guess. So if we shrink our Milky Way down to the size of a CD, the next galaxy, the next nearest, is Andromeda. And how far apart do you think these galaxies would have to be? Anyone wants to make a prediction in the... Here's where I'm going to see if you're out there. If anyone wants to make a prediction of how far apart our galaxy and Andromeda galaxy, these two, I mean, nobody's dared to do it yet. Anybody want to type? I'll give you a choice. How about this? I'll give you a choice to type in. Should we put these two galaxies 8 feet apart, 800 yards apart, or 8 miles apart? If anyone wants to type. So we have 8 miles, we have about 10 feet. So that was before I said 8 feet. I assume a net will go with 8 feet. Good. Yeah. So relative, as I briefly mentioned earlier, relative to the distances between stars, the distances between galaxies are relatively close. I mean, it's long distances, but relative to the size of a galaxy itself, galaxies are only 10s or 20s of their own diameters apart. So, and to finish our tour, our really lightning, faster than speed of light tour of the galaxy, it's galaxies all the way out. So I'm going to show you a video tour. This is an image taken by the Hubble Space Telescope with a very long exposure time, looking at a piece of the sky that we thought there was nothing there, but there's thousands of galaxies in this piece of, and I'm going to show you kind of a video tour. These are the farthest galaxies we can see. They are billions of light years away from us. The light we see from them has taken billions of years to get to us. And here's our tour, kind of a 3D tour of that galaxy field. And so with this tour, I'm going to pass the microphone and introduce our guest. Actually, let's wait and see if we have questions at this point. And then we'll introduce our guest, who is Dr. Gabriel Brammer, and he's going to talk to us a little bit about how we can see even beyond these very furthest galaxies. Are there questions at the moment? I know this is kind of a lightning fast tour of a very large topic here. So we will, of course, you'll be able to ask questions on the online Moodle, and I'm going to stop sharing my screen so that Dr. Brammer, who is the ESA Aura astronomer at STSCI at Space Telescope, welcome, and tell us a little bit about your work.
Thank you, Marion. It's a pleasure to be here to tell you a little bit about some of the recent observations that we've made with the Hubble Space Telescope, and also give some hints of why a lot of us are so excited for the launch of the James Webb Space Telescope. So can you see my screen now? Is the sharing coming up? Okay. So on the screen here, I've just got a couple of pictures of these telescopes. The Hubble, I think many, or if not all of you, have seen or would recognize a Hubble telescope. My daughter in her kindergarten class can recognize Hubble. It's amazing. And so these are more or less shown to scale with the Hubble and the James Webb Space Telescope, and this floating school bus there is to give you an idea of about how big the Hubble Space Telescope is. So Hubble has a 2.4 meter mirror sitting at the bottom of at the end of the tube there, and it has a suite of instruments that allow it to study stars and galaxies and things in our own Milky Way and planets and a lot of different things, ranging from ultraviolets to optical wavelengths that our eyes are sensitive, and even out to the near infrared. And I'll say some more about that later. And it's in low Earth orbit, so it's orbiting about 500 kilometers above the surface of the Earth, and that's why astronauts were able to visit Hubble and service it and update its instruments over its lifetime. And then on the right is a rendering of the James Webb Space Telescope, which is going to be quite a bit bigger than Hubble. It's 6.5 meters. Is the total diameter of this segmented mirror, which you can see, this sort of honeycomb shape, this gold mirror. And its instruments are predominantly infrared sensitive. So these are redder wavelengths than our eyes are sensitive to, and I'll explain why that's important in a few slides. And then the James Webb Space Telescope is going to be at an orbit at a special point in the solar system called Sun-Earth L2. So this is all, of course, within the solar system, as Mary was showing, but this is at a distance well out past the orbit of the moon, out in sort of cold not interstellar space, but cold, dark space, well away from the Earth. And so here on the left, I'm showing a picture of an actual image or set of images taken with Hubble. This is the Hubble Ultra Deep Field that we just saw a visualization of zooming in through galaxies in this image. And so each little speck that you see on this image is actually a galaxy. Some of them are somewhat like our Milky Way, others have different properties. They're all at different distances. They're all sort of seen projected on the surface of the sky. So the larger, brighter objects are typically more nearby, whereas the little specks are the very distant galaxies, going all the way out to sort of reaching pretty close to the edge of the visible universe. And on the right is a simulation of what James Webb will observe if it were to point its instruments to the same field. And so your initial impression might be, well, it looks pretty similar, and in many ways it is. But the main thing to point out about this simulated picture is just that there are quite a few more of these small little specks of blue light that you can see, which James Webb is, with its much bigger mirror, will be much more sensitive to finding these very faint and very distant objects. So though the overall view of the sky might look rather similar to what Hubble will look like in this particular way, it is going to see out further and to fainter and fainter galaxies. And so if I zoom in on one of these little galaxies in the field and show what one of these distant objects look like, on the left is a picture actually as observed by Hubble in the ultra deep field. And this is a spiral galaxy, perhaps about, I don't know, a few billion light years away. So very distant galaxy, but not all the way out to as far as Hubble can see. But you can see that even with Hubble, this galaxy doesn't look like these big, beautiful images of spiral galaxies that Mary was showing at the beginning. These are starting to be barely resolved even with Hubble's great image quality. And with the much larger mirror with James Webb, you actually have a clearer view, better resolution as you are observing these galaxies. So in my own research, I spent a lot of time looking at the shapes of these galaxies, like the pictures on the left, where you can think of it as being sort of blurry vision, that with JWST, we're going to sort of really put that into focus and really be able to measure the size and the scale of these little blue knots that are highlighted in the little cutout there. So the spatial resolution is about a factor of 2 to 3 better than even Hubble, which is sort of famous for its crystal clear images of distant objects in the sky. And so Mary showed this beautiful picture of, which is probably Hubble's most famous picture on the left there, of this Eagle Nebula. And this is taken with Hubble's instrument that's called WIFC-3, is what we call it, Wide Field Camera 3. This image is taken at optical wavelengths, sort of similar to what our own eyes are sensitive to. But this instrument on Hubble is sensitive to redder wavelengths, into the infrared. And if you look at the same part of the sky at these longer wavelengths, you see that this nebula, this Eagle Nebula, looks very different. All of a sudden, essentially what you do is you see through the nebula, where on the left you're you're sort of blocked by this bright blue and green and orange gas that is part of the nebula. When you look in the infrared, it's almost like X-ray vision in some sense. You just sort of see through this obscuring material. And so James Webb will be sensitive to these very long wavelengths of light, infrared light. And so this is more of like what James Webb would see if it were to point at the Eagle Nebula. And so certainly the view of things in our own Milky Way will look different with James Webb, like the Eagle Nebula. But it's also relevant to the very distant galaxies, which are often obscured by gas and dust. And so James Webb at the red wavelengths will also be able to see these more distant objects that might have a lot of obscuring material in them, so at all distances. And so to give a brief picture of how we study and measure these very distant galaxies with Hubble and how we're going to continue that with James Webb, I just wanted to give a little background on sort of how we estimate distances to galaxies and what they look like in these images. And the basic rule of thumb here is that in a given picture that you take with Hubble or James Webb, more and more distant galaxies appear redder to us here on Earth or in the solar system due to this expansion of the universe that Mary mentioned in the beginning of her presentation. And so these little pictures here show sets of galaxies at different distances away from us that they all might be observed in the Hubble Ultra Deep Field, but again, they're all at different distances in the field. So on the left, you see these sort of large, well-resolved spiral galaxies that might, again, be somewhat like your own Milky Way. They look kind of blue and also large because they're relatively close to us. As you go out farther and farther in the middle panel, you see, they're getting a little bit redder, a little bit smaller because, just like somebody walking down the street away from you will appear smaller the farther away that they get. They're starting to get a little red. And if you look in the rightmost panel there, the galaxies are again smaller, they're farther away, but now they're noticeably red. And again, that's not necessarily because intrinsically they're getting redder as you look further back, but just because the light that we observe coming from them has been stretched out by the expansion of the universe and just appears redder to us. And so in practice, in this field, in my research field, when we're talking about distances to galaxies, we use the terms distance and redshift more or less interchangeably because the two are very, very closely related. The redder something is, the farther away it is at these very large cosmological distances. So my own research group and I, in the last couple of years, were involved with an exciting discovery, which is now the most distant galaxy in the known that we know about. And so here's just a quick picture of how these observations work. And so the animation that I hope you can see at the bottom of the screen there is showing just a visualization of taking different pictures of a galaxy with different colors with Hubble as you go from relatively nearby to more and more distant things. And the thing to note there is that as the animation progresses, this simulated galaxy is getting farther and farther away, and it's basically starting to disappear at these blue colors in the optical wavelengths that, again, our eyes might be sensitive to. And at the sort of limit of what Hubble can observe, as you're getting close to the right side of this diagram, you might only see this galaxy or these galaxies in the very reddest colors that Hubble can observe. And that's exactly the case for this galaxy that we discovered a few years ago that we called GNZ11, which the name is not a particularly romantic name. It just refers to the field of the sky that we observed it in and something related to its distance. But this galaxy is basically at the limit of what Hubble can see, because you can see in this animation, it's only sort of visible in the very reddest end of what Hubble is sensitive to. And so its properties I've listed here and compared them to the Milky Way. So the distance of GNZ11 is at a distance of about 13.4 billion light years. And so our current understanding of the age of the universe since the Big Bang is about 13.8 billion years. And so this galaxy is something like 97%, looking at this galaxy across 97% of the universe back to the Big Bang. Of course, the Milky Way, I haven't indicated a distance there where it's sighted, like the city pictures that we saw at the beginning. And the properties of this GNZ11 are very different from our own Milky Way. So its radius, which we can measure from the Hubble images, this reddish picture that you see is actually a smooth version of what Hubble sees when it looks at this, when it takes a picture of this very distant galaxy. It has a radius of about 2,500 light years, so that's, you know, that's large astronomical distances, but it is 25 times smaller than our own Milky Way. If you sort of add up our best guess of how many of its total mass in stars, so that's not exactly the actual number of stars, but it's related. The sun is sort of an average mass star. It has 1 billion times the mass of the sun, and so it's formed a lot of stars very quickly. These billion stars it had to form in a relatively short amount of time after the Big Bang, but that's still only about 1/50th of the mass of our own Milky Way. We can also just from these pictures that we take with Hubble, determine roughly how fast this galaxy or this object is forming stars, and we estimate that to be about 25 times the mass of our sun every year. So that doesn't sound like a whole lot, but remember, we're talking about these cosmological times of millions and billions of years, and so you're able to build up many stars over this time period. And so that actually is a very high rate. Our Milky Way is relatively quiet in this respect, and so this is GNZ11 is forming stars at a rate about 50 times faster than our own Milky Way. So our Milky Way is sort of like sleeping in terms of comparing it to these very active, very early galaxies. So that's what we can observe with Hubble. But the problem here is if you want to look at galaxies just a little bit farther in what we call the cosmic dark ages, not just because we can't see them, but because this is really the era in the age of the history of the universe where the first stars and the first galaxies are forming. Galaxies really any more distant than this object GNZ11, and that corresponds to being fewer than about 300 million years after the Big Bang. No matter what you do with Hubble, these galaxies are completely invisible to Hubble because of the expansion of the light and the shifting of the light of this galaxy beyond what Hubble is sensitive to. So even if the galaxy was extremely bright at these very high distances, Hubble would not be able to see it. And so that's one of the main motivations for building James Webb and also making it sensitive to these longer and longer wavelengths of red light. And so along with being sensitive, you know, with this big mirror that James Webb can take, you can also split up the light that you get coming from these distant objects with something like a prism or other optical elements, and you can what we call disperse the light and take a spectrum of it. And so the thing to remember about a spectrum is that as opposed to just a single image, which tells us what a galaxy looks like at a single color, now we're looking at how bright an object is, it could be a star or a galaxy is, at all these different wavelengths. And so you can think of this as taking sort of hundreds or even thousands of images simultaneously of these distant objects in these different colors and then spreading that out as a function of wavelength. And so this simulated spectrum here is what we might observe for a galaxy somewhat like this GNZ11 object at a distance of perhaps only a few hundred, or about 13 billion light years, so very similar. And you can see at the bottom I've indicated where Hubble's limit is. And so, you know, these objects, even if Hubble could see that, and Hubble's not a huge telescope, so it has a very hard time taking these types of observations. You would only see the sort of left edge of this spectrum, and that contains a relatively limited amount of information. But in the next slide, I just show all the different kind of pieces of information that you can learn about these distant objects from a spectrum like this. And so at the very blue end, you learn about material around the galaxies and in between galaxies, what I call intergalactic material. You can learn about its star formation history, how rapidly is it forming stars now, how rapidly did it form stars in the past. You can learn about dust and other heavy elements that are in the galaxy, how they formed. You can study these sort of sharp, spiky features are signatures of individual atoms, or sort of many atoms, but of a given species. So, for example, oxygen and neon and hydrogen and sulfur and all these different elements that you've heard of. And that helps us understand sort of the history and the evolution of these galaxies, because of course, all of these elements most of these elements are formed by stars. And so that tells us about how stars have formed and evolved in these galaxies. And also from these very sharp features, we can also even measure motions of objects in these galaxies. So for example, if they're rotating, or just if the motions are ordered, if everything's rotating smoothly, if it's all just a jumble, that again tells us a lot about the properties and internal dynamics of these galaxies. And so in the last slide, I just wanted to give a little checklist of sort of the properties of these types of very distant objects way out to the edge of these are the first stars that sort of turned on after the Big Bang that coalesced into galaxies. On the left, I show all these properties that you might like to know to really understand these populations in detail. And really, this is sort of a color coding like a stoplight. And so with Hubble, really the object's brightness, assuming you can detect it with Hubble, is really the best thing that we can measure. And a lot of these observations with Hubble are really a matter of just counting these galaxies as a function of brightness. And that's really sort of the state of the art of what we can do with Hubble. But there's a lot more that we'd like to know. We'd like to know their sizes and shapes in more detail. We'd like to know their distances very precisely. We'd like to know about how they form stars and how they're forming stars, and also even more details about how their material has been enriched by these stars, and also these dynamics. And so, these things, some of these things at the bottom there shown in red, Hubble can't even do if it wanted to. But all of these kind of observations will be made from James Webb. So not only will we be able to just detect these extremely distant objects, but we'll be able to study them and understand, put them in a real context in much more detail. So thank you.
Thanks, Gabe. So, wow. So JWST is going to give us a lot more information. If anybody has questions at this point, I want to stop for a moment and let people use the chat or unmute themselves if they have any. Okay, again, if as you kind of go away from this and you think of questions either for Gabe or for the rest of the tour, please feel free to post them in the Moodle, and we will make sure those questions get answered. I'm going to go back to sharing my screen and address a question that let's see. Dr. J asked, saying, well, what's gravity have to do? Because, of course, the tour of the universe that I gave was very static. It was as if all these structures that we were exploring were just standing still out there, and constant in time. But of course, we know that the galaxies are moving, that stars and galaxies evolve, as Gabe was talking about. And I didn't really touch on that, the dynamics of the universe, how things form and evolve and how they change. And with regard to your specific question, Dr. J, around gravity, of course, those galaxies that are relatively close together, let's see if I can. When their galaxies sometimes are in clusters, in which case they're close enough that their gravity pulls them together, holds them together in these clusters that are, of course, moving. But as Hubble found in the 1920s, the farther you look out, on average, the further galaxies are away, the more they appear to be moving away from each other and from us. And so there's local groups in which galaxies are holding together in clusters with their own gravity, but there's this other characteristic of empty space, that it's expanding. And so the tour of the universe that I gave you was actually a tour of what is now known to be a mere 5% of what makes up the universe. All those galaxies, stars, gas, dust, planets, people, protons, electrons, particles, subatomic particles that we know about and can detect through all our instruments directly through their emission of light, is really only 5%, because, and the way we know that is that we see that the movement of galaxies appears to indicate they're made of much more mass than we can, if you counted up all their stars and gas and dust, they're actually rotating and moving, and we call that dark matter. And then when we look at the expansion of the universe, it's been discovered within the last 20 years that the space between those galaxies is expanding and expanding faster and faster, accelerating over time. And the quantity, which both these things will be explored more by hopefully by actually subject matter experts rather than we haven't touched on those at all. So Dr. J, yes, gravity is a key player in understanding how the universe evolves over time. But in today's webinar, I really touched on just the kind of starting to get your mind around size and scale. As Gabe talked about, once you start looking at the very furthest galaxies, you really have to think about time and the expansion of the universe. There's a question. We have a couple questions for you, Gabe. One is since GNZ 11 is the furthest galaxy and therefore the youngest in terms of light, what does its structure tell us about the evolution of galaxies? Do they start out large and then condense to the size of the Milky Way?
Yeah, that's a very good question. So as I mentioned, the GNZ 11 is quite a bit smaller than our own Milky Way, so it's about only a 50th of the total mass, and it's quite a bit smaller in size. But it is true that galaxies like that, we do think, will eventually turn in and evolve to form galaxies somewhat like our own Milky Way. One of the surprising things about GNZ 11 is actually how big it is. This billion solar masses already that have formed very early on is somewhat faster than we had been expecting based on models and our understanding previously. So it's probably going to be the case that an object like this will form and later in its evolution will actually be something somewhat different than the Milky Way, like a big galaxy and a big massive cluster or something. But it's very true that we do think that these sort of small building blocks, these things like GNZ 11 that are much significantly smaller than the galaxies we see today, they're sort of like little Lego pieces that through gravity and mergers and just continually forming stars will eventually become larger galaxies, very much like our own Milky Way.
Thanks, Gabe. And Annette, to answer your question, related in terms of are there different kinds of galaxies than spiral, as Gabe just indicated, kind of broadly, we think of three kinds of galaxies: spiral galaxies, galaxies that are called elliptical, which really don't have that spiral. They're much bigger typically than spiral galaxies. They don't have that nice spiral structure. They're kind of big egg-shaped things. And then a third category called irregular, which you might throw in GNZ 11 or these forming galaxies, which is galaxies that might be colliding, or they're oddly shaped. They look kind of messy, and so they're in this category called irregular. There are fine refinements to those categories, but okay. Good. I think I'm going to now, we've given you a lot of content to think about. So now Tim's going to introduce you to some of the resources that are connected to this very mind-expanding content.
All right, and you guys all should still see the slideshow here. So there are a lot of things that we've got that are related to this. I'll give you a link to that wonderful visualization that Mary shared a little bit earlier. A few other things. For example, right here, Visions of the Universe exhibit. This is an exhibit that basically brings people through a tour of the universe, from the planets to stars to star clusters to galaxies and beyond. This exhibit is actually available online, and I will show you the website right here. So if you navigate to this website, which the link is in that slideshow, which is available after the webinar, you can go to each of these 12 panels. I'll pick this one. And on here, you can download a high-res PDF, which will actually print out to 19 by 34 inches. And you can use that for an exhibit. You can use that for activities, whatever you think you'd like to do. We'd love to see how these can be used in new different ways. We also have 12 copies of these panels, which are about 6 foot high, down in the basement here at Space Telescope, and they are available to be sent out to anybody who wants them. You do have to pay for the shipping of the panels from here in Baltimore to wherever you are and back, but otherwise they're free for your use. If you send me a note, either through my email, which I believe you have, or through the Moodle, either way, I'll be able to help you get a hold of those. We've also mentioned, you've seen all of these gorgeous pictures that Mary's been putting up. We mentioned AstroPix last week. I'm going to mention it again very briefly here. You can find many, many images with lots of information on them. And there's a little search function in case, say, you wanted to find a shot of a galaxy. And there it goes. And you'll get all of these wonderful pictures. And I'm just going to click on this one. Mary mentioned the NGC series earlier. This is NGC 5949. It comes in all sorts of different resolutions, which you can access very easily here. There's also a lovely little link. If any of you have ever used Worldwide Telescope before, this will send you directly to Worldwide Telescope, which gives you a map of the sky. And as it takes a moment to warm up, it should navigate right to this particular object and show this image in its place in the sky. There it goes. This one's located in Draco, and it's going to zoom in, and you'll be able to see about how big this image actually is in the sky. And one of the things I like about this image, we were talking about its galaxies all the way back. Well, if you look over in the corner here, you can see a couple of those more distant, redder galaxies further in the background here of this particular image. And you'll notice those background galaxies in a lot of the different Hubble shots that are out there. So let me go back to the show. And where are we? Here we go. So that was AstroPix. I'm going to mention a couple other ones very briefly. You can look through the, I know we're getting short on time, you can look through the slideshow and find links to these. The links are also up on the Moodle. Henrietta Leavitt's plates got mentioned earlier. You can actually access the plates that were studied by the Harvard calculators on the web, and you can actually look through some of the plates yourself if you go to this website, the Astronomical Photographic Plate Collection. If you go to Dash in here, you'll be able to find a link to access the plates themselves. Right here, we have, I'm going to play this. There's a series of videos produced by Harvard Smithsonian. They're originally on DVD. They're now available online. There are a number of key concept videos and evidence videos, ranging from our universe is made to galaxy to how do we know the age of our universe. There are research videos talking with scientists who've done some of this work and much more. And there's some really gorgeous, I'm looking over at my screen while I've got this. There's some really gorgeous imagery, visualizations going through. You can go ahead and explore these on your own. I'd love to know how you might be able to use some of these with your audience. All right. Here we have the visualization on the right that Mary was showing earlier, and there's another one that was made down the hall. Both of these were made here at Space Telescope. The one on the left was actually used to make an IMAX film, which perhaps some of you are showing, Hubble, Galaxies Across Space and Time. These visualizations and many more are available at the svs.gsfc.nasa.gov site. That's the Goddard's Visualization Studio. And there are a ton of really wonderful visualizations there on all sorts of topics that you can explore and hopefully find new ways to use. All right, there are a few others here. Night Sky Network has produced guides and toolkits. Our Galaxy, Our Universe actually goes through what the universe is made of, has some scale models. There are videos available that you can use to explore the topic with your own educators in-house, or you might use them to figure out how to talk about these issues with your audience directly. Night Sky Network is not a NASA organization, but it does get a lot of support from NASA, and the creation of most of the outreach sources that you find here were all funded by NASA. This, How Big is the Universe, is a legacy product made by the NASA Smithsonian Education Forum. It's a printable or an online tour of how big the universe is. There's a lovely cosmic distance scale made by some folks at Goddard, not using scientific notation, so though you get nice long numbers with lots of zeros that might make a little more sense to your average audience member. And there's also, we were talking about the role of women in science with Henrietta Leavitt and Caroline Herschel. If you're looking for some other women in STEM, there are some other figures you can access some information about at this website here. So I'm going to let Erica finish up talking about the next steps before our next webinar.
All right. Hopefully everybody can hear me. Okay. So we've just finished our second webinar, Putting the Universe in Context. We're making a nice headway onto our next one, which will be in 2 weeks on September 13th. It'll be Understanding the Electromagnetic Spectrum. So getting a little bit more into how we know these things about the universe. Following that, we're going to start getting into our next big question of how did we get here? So a little more deep into looking out is looking back in time. So more about that redshift and what we're seeing out there. And following that, a dynamic universe, as Dr. J asked about, more about how gravity plays a role in understanding the universe and motion. Okay, next slide, Tim. All right, so your immediate next steps. We've got another discussion topic that we're going to be posting in the weekly discussion topics on the forum. This one will be about understanding the universe. What we want to know is what's an idea or a concept of the universe that you find mind-blowing? Maybe something Mary shared or something you know yourself. And then what are some of those questions you think your visitors or audiences might have about the universe beyond our solar system? So we really want to hear from you on the portal, get these discussions going. We're also going to start a discussion about the resources that you find on the Moodle and that we share through these webinars. So if you want to take a search through some of the things that we've posted, shared in past webinars, dive down into our resources, we're going to start a forum on under the Affiliations forum, a discussion where you can share something that you find engaging and let us know about it. And then our next big step is the next webinar. Like I said, on September 13th, we'll be diving into understanding the electromagnetic spectrum. And we will hopefully have a guest specialist for you that week as well, and we'll let you know as we get a little closer.